Hello, welcome back. Today we are doing Paul Hewitt's Conceptual Physics, Chapter 19 on liquids. I hope you all had a good Christmas break. It was a nice long break. All right, let's get back to it. Okay, fluids. So the Earth is wrapped in fluids. Note I use the word fluid. Gas is a fluid and liquid is a fluid. This lecture will be on liquids, which are a type of fluid. The Earth is wrapped in fluids. That first we have that layer of water, that's a liquid fluid, and then we have another fluid around it, that's our atmosphere, and that is a gas fluid. So fluids are very important. They affect our daily life all the time because we are in a sea of air, and if you live near the ocean or something, you interact with the sea. Okay, so first we're going to talk a little bit about our old friend pressure. Remember, pressure is force over area. So if you remember pressure, like how much force is pushed, against you by something. So pressure, force over area. If someone punched me, the area would be the cross-section of the fist. The force was how hard they pushed with that. Now, if I'm punching someone, so I've got that area, that they feel if I give more force, it's a higher pressure. Higher pressure punch will hurt more. The more force I give it, right? Because the bigger this F, the more force I give that punch, the bigger this F, the bigger this P, right? Because it's up in the numerator. Now, if I give less force, the pressure of that punch will be a lot smaller if I'm pulling my punch, if I'm not really punching as hard as I can. Area we call it, so force and pressure we say are correlated here. Are related here. Pressure and area are what we call inversely related, and that means they're opposite. So here, if I give that punch, right, the pressure is divided by the area of my fist. Now if I put a knife in my fist and I give that punch, now like the punch I did without the knife and with the knife, it's the same amount of force with my punch. But what I just did here with the knife is I decreased the area from this part of my knuckle that's hitting someone. I've decreased it now to imagine a knife. It's even smaller than this. Very, very tiny. And remember, when we divide anything by a tiny, tiny little number, so as you can imagine, if we divide it by a tiny little number, this thing gets huge. This thing getting divided by a tiny little number gets huge. Let's say the force is 10. We're not doing units, just for the sake. And say that the area of my fist, let's just say, is 1. The cross section is the area of my fist. So then the pressure will be a 10. Now I'll say that now I'm holding a knife, and the area of that knife, let's say, is tiny. Now all of a sudden the pressure is 1,000. So this is basically all melee weapons deal with the pressure, equals force over area. Force over area. Now we're going to talk about liquid pressure. So liquids put a pressure on the thing that they're in. So let's give an example here, or before we get to that. Okay, so to give a little less violent example, I put a book on the table, right? There's a certain pressure that if a little bug was trapped under that book, the bug would feel the pressure, right? There's certain pressure I'm putting on that book, on that book here, on the table here. I'm putting a pressure by putting this book here. This is the area. You can imagine the area, and the force is the weight of the book, right? The weight of the book, the force of gravity on that book, pulling down, and the pressure, divided by the area of that table. And as you can see, if I stack it really tall with many, many books, so here, let's actually draw 2 different tables. So you can imagine if you were a little tiny person underneath that book, if you stack many books, the force is much greater, right? You got it here. The pressure. So you want to go get a cough drop. Oh, sorry. If pressure is force over area. In this case, the pressure is bigger, not because the area is bigger, we have it on a neat little stack here, but because the force is much bigger, because now we got the force of gravity on all those books. Okay? Likewise, the pressure, now instead of saying this is a book, now we're going to say this is a basin of water. Okay? Now we're going to say this basin of water weighs just as much. We really need a blue, let's just say this is, okay, a basin of green liquid. We'll say green liquid because I don't have a blue marker here. Okay? As you can imagine, this is still putting pressure on the bottom, or we can say the table, or we can even say the bottom of that container, right? So we just glue the bottom of that container to the table, and we'll just consider the same thing right now. The weight of those, remember the weight of that book on this, the force over the area that was exerting a pressure right there on the table. Now this is the weight of the water, okay? Weight of the water, think of all that water, the weight of all that water, there's a certain pressure pushing down on the bottom of that container. Now imagine all these books are replaced with water or green liquid, okay? So you've got all this liquid. You can imagine if you're a little underwater person, instead of a little person being trapped by the book, you're a little underwater person here. You will feel the weight of all that liquid, all that water on you is much greater when there's more water, right? This applies to dams, things like that. It also applies to, if you've ever seen this experiment, well, they'll take a tin can, it's like a tin can like this, say. So you've got a tin can, and they'll fill it up with water. And then, I should say water. They fill it up with water. If you've ever seen a tin can like this, and then they'll punch with a nail, like a hole, here, here, and here. And you'll watch the streams of water shoot out. And this one, it will look kind of like this. This one will usually shoot farther, and the guy in the bottom will shoot the farthest. And when you compare, when you think about the pressure you would feel at the bottom of this, the pressure you feel at the bottom of this, you can see why. Is that this guy, the pressure isn't as bad. He only has to deal with the weight of all the water above him. See? That's all he's dealing with. From this guy's perspective, he doesn't know about the rest of the... For all he knows, this is the bottom of the can, right? And this is what he's spraying out. This guy can feel the hole here. When you're at this pressure, you can feel the weight of all this water. Okay? So he's feeling much more pressure, and he's shooting out farther at the higher pressure. And here, at the way bottom of the can, he feels the weight of all that water, and he shoots out way farther. This is why, when they build dams, so say we've got a big lake here, big wide, huge lake. We've got a little dam here. It's holding it back, okay? This is the mountain, okay? Now let's suppose we've got a very small lake, but it's deep. And we have a dam like this. So say we have this small lake, like the volume of water behind this dam is much greater. Maybe I should exaggerate that a little more so you can see the difference. Okay, so the volume of water behind the dam A is much bigger than dam B. Okay, we'll call this dam B, this is dam A. However, dam B has to be much, much stronger than dam A, because dam A is only dealing with, if you look at the depth, this much pressure, think about on the tin can, like that kind of pressure. Where dam B has to, especially down here at the bottom, it has to deal with that kind of pressure. So how strong you build your dam doesn't actually have to do with the total amount of water. Because if you think about it, all this area here is helping support that, you know? What matters when you're building this little guy here is just the depth of the water. And so the equation is that the pressure experienced from a liquid, the pressure experienced here, I'll just work this. The pressure, the liquid pressure, the pressure, I'm gonna write pressure from a liquid, so we know that's what from a liquid is equal to the density. This is a funny symbol for density, rho, we call that rho. And that is the symbol for density. So if you remember density from last week, we talked about density is like how much stuff there is in a given amount of volume. So, example, the density of metal, of lead, is much, like you get a lot more stuff if you have 1 little centimeter cube of lead. If you have a little centimeter cube of a marshmallow, it might take up the same volume as a centimeter cube of lead, but you have a lot less stuff there. It's a much lower density. Okay, so this is density. So the density of whatever liquid it is times the depth. That is the pressure, the liquid pressure that you're going to feel. So you can see here, the depth is much greater. And the liquid density, so water has a density, oil has a density, liquid mercury has a density. Every liquid has a density. I mean, everything has a density. So here, if you see, if that dam that was meant for water is now holding back molten lead, and let's just pretend for now that the heat doesn't matter. We're not worrying about our dam melting. If it's holding back molten lead, that is a lot more pressure. Why? Because we just increased this. The density of molten lead is much, much greater than the density of water. Okay, so now we're going to talk about the buoyant force. And I know you've all felt it. You go into a swimming pool and you just feel lighter. Like you just feel it. And that has to do with this. The reason you can feel that pushing you up all has to do with depth. So I'm going to give an example of, let's say there is, let's just make it bigger so you can see. You're in a swimming pool. Okay, so here's a swimming pool. And just to make it simpler on us, let's imagine it's one of those above ground swimming pools. Okay, so this is one of those above ground swimming pools. You can imagine if you poked a hole the side of the above ground swimming pool, like right here, you probably get water looking like this. If you poked a hole near the bottom of that swimming pool, that water would come shooting out like that. I mean, actually, this is why water towers, where they have those big, if you ever see those funky water towers that look like this, kind of like on top of hills, and you see them on top of hills. The reason here is they're trying to increase that depth. So by the time it gets into your house, and you turn on the faucet or the hose, it'll come shooting out for you. It's because they're trying to increase that depth to increase the pressure. People don't like it when they have low water pressure. They don't like it when they turn on their faucet or their hose and it just comes dribbling out. They want it to come squirting out like this, not dribbling out like that. So that's why they make water towers. But anyways, so back to this example. So you're in a pool. This is buoyant force. You're in a pool, and let's say you put a block of foam or something in here. Okay, so we're going to imagine this block. I'm just going to put it down here. Okay, so we'll consider. Let's first consider this block, and then we'll consider the other block. Okay, so pressure. Remember, that water is going to be pushing. So we've got pressure here. From this depth. Remember, this is medium pressure depth. Remember, this is high pressure. It comes shooting out of the can. This is like medium pressure. Okay, so we've got medium pressure. So I'm going to draw these size arrows. The arrows are showing. And now I've got really on this bottom of it though, we're deeper down. So we've got big pressure on the bottom of that, okay? And then we've got, from smaller pressure to bigger pressure as we get deeper. Now, if you remember from first semester, we talk about forces canceling each other. That if you are pushing really, really, really hard on one side of something and someone else is pushing, it's not moving if you're perfectly balanced. If you've seen a perfectly balanced tug of war game, someone can be pulling with all their might, and if they're perfectly balanced with someone pulling all their might on the other side, the rope isn't moving. So this is what's going on here. The pressure on these sides of the box don't really matter because they're perfectly canceled out. We know that the pressure on this side is exactly the same as the pressure on this side because remember, the pressure depends on the depth. And so here, these are going to perfectly cancel out. So the box isn't going to even feel it. Here, perfectly canceled out, right, because at the same depth. Here, perfectly canceled out, same depth. So it's like that tug of war, it has no effect because it's perfectly balanced on both sides. But we see here, the pressure against this side of the box, at the top of the box, because it's medium pressure, this is lower pressure, medium pressure, high pressure, this part will be canceled by half of these, but not all. So by the time we're done canceling out all the who balances who, we still end up with a bit of that water pressure pushing the box up. This is the buoyant force. This is why when you go into the pool, you feel lighter, because you are lighter by that little bit of that pressure that was not canceled out that's pushing you up. Okay, now you may ask, well, how much? We know how much this pressure is that's pushing us up. We actually can. There was a genius, Archimedes, way back, Greek guy. Archimedes discovered that basically the buoyant force that you feel pushing you up will be the same as the, let me make sure I'm reading this right. The buoyant force will be the same as the weight of the water that you have displaced. So when this box is in here, basically this volume of water, that volume of water, if you weigh that volume, equivalent volume of water, that is the buoyant force that's left pushing you up. So when you get in the pool and you feel that buoyant force, you just feel lighter. You are lighter by the volume. If you make a human replica of you made out of water, by that volume, that weight of water that you are being pushed up by. Okay, so let's see. Now you can oh right. So this is why fish don't sink. Sorry. So you may ask, well, why do some things still sink if there's a buoyant force? That is because gravity hasn't left. Gravity is still pulling you down. So when we say, does something float or does something sink? So you've got these guys pushing up, you've got gravity pulling you down. Basically, the difference between objects that float and objects that sink is if the gravity force is greater and cancels out the buoyant force enough that it's still sinking, or if this force, the buoyant force, is greater than gravity pulling on it. So for example, a beach ball. Or a floaty, if you've got a beach ball, gravity is still pulling on that beach ball, but remember, gravity only pulls on something. The force of gravity on an object, remember, is the gravitational constant times the mass of that object. So obviously a beach ball is not very massive versus like a lead weight. So if you had a beach ball and a beach ball made out of solid lead, and you put them in the water at the same time, the beach ball made out of solid lead is going to go and sit to the bottom of the pool. That's not that the lead beach ball doesn't have a buoyant force on it. It does have a buoyant force on it. It's just kind of small compared to the force of gravity. So if something sinks or floats, has to do with if that volume of water that it's displacing the volume of water that it's displacing, does that give it enough of a buoyant force? Is the weight of that water, the force, that weight of that water, following Archimedes' principle, enough to balance and be better, counteract the pull of gravity on that object? Okay. So everything is a buoyant force, even things that are lead. Archimedes was famous for figuring out that you could find the volume of even a irregular object by if you get a perfectly full basin of water and you put your irregular object, and water will spill out, right? If your basin of water is perfectly level, and then you put your object in and water will spill out, you displace that amount, and then you can gather up the water that spilled, and that will tell you what your volume was in water, because liquids like water, etc., liquids are almost incompressible. So they pretty much will show you the exact volume of the thing that you put in. Liquids, not fluids, because we'll talk about gas later. Gas is compressible, but liquids are almost incompressible because remember, all the little atoms are just like flowing over each other. Okay. So, okay. Something that's pretty cool when we talk about things floating, we don't usually think of this, but mountains are kind of floating. Because remember, we've got all that magma, all that molten rock. So if you imagine mountains are sort of, we think of an iceberg floating. So if you think of an iceberg floating in the ocean, as you know, icebergs often like stick up like that. And the reason is because ice is a little bit, sorry, it's late. I'm just gonna get my brain to get it. Float, here, you've all seen ice floating and whatnot. So with icebergs, if you decide to shave off some of that iceberg, like cut off this much of the iceberg, what will happen? The entire iceberg will shift up, right? And now you have it's still sticking out. It's just not hanging as low in the water. And if you're like, well, I'll cut that part off too, then the whole thing will float up and it will always basically have something sticking out. So in the same way, well, not always, I guess it gets, anyway, proportionally less as it goes up and up and up, just like an ice cube, and it's barely sticking out. But anyways, as you can see, an iceberg will go up as you shave it off. It'll just keep floating higher because now the iceberg weighs less, and so it'll float higher and higher. In the same way, mountains floating in magma, let's say the molten rock of the Earth's crust, is that even if you were to wear away almost like all of this much of the mountain, we wouldn't really notice, because the mountain, in the same way that the iceberg will float up higher, the mountain will float up higher in the magma. Because mountains, what we see as mountains, are just like the tip of the iceberg. I like the line in Jonah, when Jonah talks about, to the roots of the mountains I sank down, in the deep beneath barred me in forever. It's just that line, the roots of the mountains. Mountains have roots. Mountains go way, way, way down. We just see the tips, like the way you see the tips of the iceberg. So that was pretty cool that mountains float on a sea of magma. Okay. So the submerged object has a buoyant force that is dependent on its volume, not its weight. This is important. This is why if you take a beach ball and you throw it in to the pool, it'll just sort of float, and it will actually only displace like a little bit of water. You know what I mean? Like this much water. It'll float high. Why? Because that little bit of water that it displaced, like this little bit amount, that's enough to cover, that's like the weight of the beach ball, is the volume of the beach ball, is the weight of the beach ball. Now let's say we tied some rocks to that beach ball. If you tied some rocks to that beach ball, now say it's going to float lower in the water, somehow attaching a rock to it, because its weight, now it needs to displace this much water, do you see, in order to balance, to get the buoyant force, because remember that the buoyant force on it is equal to the amount of water that it displaces. But the volume. Now imagine that you filled up that beach ball with sand. It's going to sink down to the bottom there, because it's still displacing this much, but like as we said, too much gravity here. Now, but it's not about weight, it's about volume. Because now imagine we took that beach ball and we didn't blow it up, okay? You let all the air out, you compressed it, it's a little wad of plastic. You threw it into this is our little deflated beach ball, okay? You threw it into the pool and it just sinks down to the bottom. Why? Even though it weighs the same, without the weight, even though it weighs the same, so you get two identical beach balls, you blow one up with air, and you crumple up the other one and throw it in. They weigh the same, but this guy doesn't have enough volume to displace the amount of water to give it the buoyant force to hold up, and so it goes down to the bottom of the pool. This is all naval warfare trying to sink each other's ships. So, for an example, does a boat sink or float? So now we're going to think about an ocean. So we're going to think about an ocean. Okay, Atlantic Ocean. And you got a boat, okay? And you made it out of metal. So technically you're like, whoa, metal things sink, right? Except that, you made it. So we're looking at the boat like cross-section, okay? So we're looking at the prow, okay? Look at that boat. So, as you can see, the boat is displacing this much water. See, it's displacing that. What's inside the boat? Well, even though it's made out of metal, the density of the boat is actually quite low because it's full of air. It's full of men and air. People and air and cargo. This is why you don't want to overload your boat with cargo. Because the more cargo you pack in your boat, the higher the density of your boat is. Also, the more gravity pulls on your boat. And your boat will sink down. I'm just going to read it. Oh, it's easier to just redraw the sea. So if you overload the cargo on your boat, you can see I'm still floating. I still made it. But now we tip a little bit. We get water in then the water will fill up all the empty, air pockets, and then we go down. We don't want that. This is why in Jonah, when they get in a storm and the storm tips your boat back and forth violently where water can get in Jonah, the sailors throw all the cargo overboard. Because what they're trying to do is as they ditch their cargo, it'll shoot their boat up. It'll ride higher in the water. And now they have more, they can tip farther without the water getting into their boat. This is also why in naval warfare, with cannons, the days of cannons and all that, you try to shoot a hole in the side of someone's boat. Because look, the boat, what this will do, you shoot a hole in the side of the boat, the water rushes in, starts filling up with the air pockets, the density of the boat goes up. So this means, gravity is pulling on the boat more, boat density goes up, boat is sinking down. It's like filling up that beach ball with sand. It goes down. So if you think about it, it all has to do with density. And that boats use air to basically fluff up their density. Another way that we think about this a lot is in submarines. Wait, let me see, did I write that on the notes? So submarines, this is probably the world's worst drawing of a submarine, but you don't quite look like that, but you get the idea. And they have these ballast tanks on the side. So here you've got air, you've got your men in here, your control room, little periscope, right? They have those. You got your little propellers, your little wheels. But your propeller can only make you go this way and this way. If you want to go up or down in your submarine, you fill up your ballast with water, and that makes you dive. That makes you go down because you're denser. And so now that you're denser, gravity, the force of gravity, remember the force of gravity pulling on you is mass times the gravitational constant. So you're more massive when you're more dense, you've got more water here, you're going down, and your buoyant force stays the same. Your buoyant force is just dependent on your volume. So remember, the buoyant force on you is dependent on your volume, and so that just is the same. And when you fill up your ballast tanks with water, you dive. And then when they get rid of the water, I guess they must let air out of the main cabin in. When they're down into the sea, when they let air of the main cabin in and squirt the water out, now they must have pressurized air in there. But anyways, now that your ballasts are empty, now you're lighter, you're fluffier, same amount of volume, same buoyant force, but now the buoyant force is greater than gravity pulling you down, and you go up. And that's how a submarine comes up. By emptying the ballast, by letting the air, I guess, from its main cabin into its ballast tanks, and it goes up. Okay, fish. So fish have about the exact same density as water. I mean, they're mostly made of water. And so because fish have almost exact same density of water, fish, just their buoyant force, remember the buoyant force acting on them, is equivalent to the amount of water that they displace. So that means that for fish, the force of gravity pulling them down and the buoyant force pushing them up perfectly balances because they have the same density as water. And so the fish just sort of hang out. Now, when dead fish, often chemical reactions go on and they start bloating with like gas discharge and whatnot, dead fish will float. That's why you see dead fish floating on the surface of the water, or at least the bloated dead fish do. A living fish has about the same density of water, and that's why it will not sink or float. It just is. I mean, it can swim, with its little fins and whatnot, but it just is. Okay, so we did the fish density. Oh, and another example is if the fish decides to eat a bunch of rocks, he will sink lower, right? Because now he's denser than water. Alligators, or was it crocodiles? It's either alligator or crocodiles. They actually do this on purpose. If you see a alligator, like you see the eyes, I think they have a picture of your book, and you see the snout, and you usually see like the spine. Sorry. If you're looking from above and the tail sort of sticking out, but alligators like to stay under the water. So alligators, when they found, I think it's alligators, it might be crocodiles. Crocodiles are way worse than alligators. They eat a lot more people. But either crocodiles or alligators, whoever these creatures are, when they eat rocks to make themselves, if we have a side view, to make themselves less obvious, that all you see now is the eye and a little bit of snout. Because the rest of them, there's more submerged under the water. It's exactly like a submarine filling up its ballast tanks with water to try to sink down. So if you look on profile of an alligator, okay, this is not a good picture. Okay, let's see. Profile. And the alligator knows this much of him is gonna float. So he eat rocks, he increases his density, and now he sinks down lower, and it's harder to see him. So That was kind of creepy. They're that smart. Okay. So now we are going to talk about not drowning. So if you are in water and you want to float, you don't want to go down, what can you do? Well, just like the submarine wanting to, fill up its ballast tanks with air, what you want to do is decrease your density. So you want to increase your volume and decrease your density. And how you do that is by filling up your lungs with air. And when you fill up your lungs with air, you make yourself like that beach ball that's getting inflated. You make your volume bigger, and when your volume is bigger, you're displacing more water, so your buoyant force is greater, and you are making yourself less dense than the surrounding stuff. That will make you float. So you fill up your lungs. Another thing you can do is wear floaties. So when moms put all those little floaties on their kids, that increases the kid's volume and decreases the kid's density, because these things are all filled with air. That's what a life jacket does. Life jacket's made out of foam. Foam is just a lot of trapped air inside plastic or whatever that stuff is. And so that, again, your life jacket is bulky life jackets. They're supposed to be bulky on purpose. They increase your volume and they decrease your density. That's how they work. Okay. And last thing is we were just going to talk about hydraulic presses. Jenny, is it still running?
Yep, it's
okay.
still running.
So a hydraulic press, they use these when they're lifting cars or whatnot. So remember we talked about how the pressure in the liquid is equivalent to, rho times density, but in this case, the equation we care about is the force over area, right? This is the pressure. So what we can do, what they found out we can do, is we know that the pressure will be the same, right? So we've got here, and we have a really wide one. Let's say we've got a plate. I think the book has an example of like a little plate and a little plate here. You know that if you push down on this guy is going to shove up much, much higher for the bit that you push here. It's a force multiplier. It's the same principle as using a lever. Because you'll see that here, because the pressure that you need to exert here, the area is much bigger. So because it's a liquid and liquids are almost not compressible, the pressure is going to be the same throughout the liquid. So then here you can, because there's a big area, and suppose you do, so the pressure here is going to be the same as the pressure here. I'm going to do pressure 1 and pressure 2. Okay? And so now we've got pressure 1. So pressure 1 equals force 1 over area 1 is going to be the same as pressure 2, which is force 2 over area 2. And so, as you can see, this area is much bigger, this area is much smaller. Wait, I should probably rearrange that. The pressures are the same. And so, as you can see, because this is a big area, this is a big force. Wait, okay. This is not the clearest way to do it. Well, basically, as you can see, this has a bigger area, and so even if you just have to push it down like a little bit, you push it down a little bit, here this is going to shoot up much, much higher. And this is how hydraulic presses work, because the pressure is all the same throughout. And so in your book, I think on the last page of chapter 19, there's a very good example of how those automobile lifts work. And if you've got a little tiny narrow lift here, like just pushing this down a little bit, you can get this to squirt way up. And it's because the pressure is the same throughout the liquid, and all that pressure against a little tiny piston versus the giant piston, you can just push a little bit on the giant piston, and your little piston is going to shoot way, way, way out. Okay. All right, that's it for chapter 19. Thanks. Jenny, can you shut it down? You can shut it down.
Oh, sure.
Sorry.
Bye, everyone.